So not as usual. You do not have homework due this Friday. Your chapter 10 homework is not due until next week on Friday. I am planning to get close to finishing it today, but certainly not all the way there. So we'll probably finish chapter 10 next Tuesday. Chapter 10, that's what we're on. Yeah. But hopefully we can start chapter 11 after that. I don't want to talk a lot about it, but I do want to say that we are going to start talking about the project next week, and there will be an the first assignment will be open next week, where I will force you to choose what topic your presentation will be over. And if you go to the week 8 section, you'll see like this project topic choice, and it's set to open this Sunday at midnight. And the thing is, it's a first come, first serve sort of thing. So I listed out, there's a whole bunch of topics listed. Some of them we've covered, some of them we haven't covered. Some of them are super interesting. None of them are super boring. I say that as a physics professor. But only 3 people can choose each topic. So like electric fields always get chosen immediately because we've already done that. But only up to 3 people can choose each thing. So if there's something in particular that you want to make sure you get, I would look at that on Monday and just kind of look through the topics. Does that make sense? I'm planning to talk about this just in length next week. I freed up some time to do that, but I did want you to let y'all know that there is like this topic choice. It's a first come, first serve. So if on Tuesday the thing you really wanted to do is taken, that's just the way life is. Sound okay? Okay. Okay, so I think that was everything. Great. Yeah. Chapter 10 due next Friday. There's going to be a quiz open this weekend. It will cover up to Kirchhoff's laws. So we'll finish that today. It will not cover RC circuits. I actually plan to start those today, but that's not going to be on the quiz. Just Kirchhoff's laws. Okay. Any questions?
From what I heard she tried, but
it all somewhat makes sense then?
I don't know.
Did he try?
Okay, if it all makes sense, let's get into the physics.
What are you trying to
do? So I believe we left off last time. We had defined the 2 Kirchhoff's laws, which were the junction rule, junction rule, where at any spots on the circuit, the current going into that spot had to equal the current going out of that spot. And that includes if there's splits in the wires or anything. And then, sorry, that one. And then there was the loop rule, where if you can trace a loop through a circuit, the changes in voltage throughout that circuit have to all add up to 0. So whatever voltage you gain need to be cancels out by the voltages you drop. And I think we did like a really super simple example. And I'd like to start off with a more complicated example. So from your homework, number 17 is actually a very complicated example. So this circuit has several resistors, 2 batteries, and various pathways. Okay, and we can label these things. I have this one's battery 1 up here. So EMF 1, this guy's EMF 2. I have R1, and then I have a capital R1. I have a capital R2. I have a lowercase r2. And I have a capital R3. And we're given values for all of these things. That may be R1. We'll see. R2, 2.5 ohms, R3, 1.5 ohm, R1, little r1 equals little r2 equals half an ohm. And so I'm hoping you see these little r's. That's actually the resistance of the battery. So when you see this little resistor right next to the battery, that's usually telling you that they're trying to model an internal resistance of a battery. What else do I have? I have some battery voltage, 18 volts, and 45 volts. Okay. So what we're going to want to do is we're going to want to find the current through various spots in the circuit. And this is an example of where just finding an equivalent resistance and trying to like piecemeal it is going to fall apart. Because while we totally could find a lot of equivalent resistances for my resistors here, what's going to throw it off is this extra battery. Because since it's sending off different currents in different directions, we can't always say that, you know, if we can't say this is equivalent to a battery with an equivalent resistor hooked up to it, because I have various batteries hooked up in various ways. Does that kind of make sense? Okay. So instead of doing that, we will discuss this as a Kirchhoff problem. Now, generally, with a Kirchhoff problem, you get to assign the directions of the current. And I think we talked about this on Tuesday, where you would just choose some directions, and as long as you're consistent, you'll get the right answer. And that's generally a good first step. Now they give us the directions of some currents, or at least the conventional directions. So we're going to use the ones that they came up with. I don't know if they're the correct direction or not, but if we get a negative answer, we'll know that they're not. So when you're assigning currents, basically what you're looking for is you need to make sure you have a label for a current for each different branch. So you go to the junctions, and so here I have a junction. And I label all the currents going in, and I label all the currents going out. Now I might have to split up the current further depending on the circuit, but for this circuit, this is all that's necessary. Because you notice if you follow I3 around, it takes you to this next junction. And if you follow I2 around, it takes you to this next junction. And I1 is going to be the same way. So for all the junctions in this circuit, we have defined all the currents. If you had a situation where like you had an extra loop like that, or so now you have like these two resistors, you'd have to define an extra current for that one. Sound okay? Okay. Okie dokie. So first off, let's write down the junction rule for this. In particular, let's start over there on that junction. So what current is going into that junction? What do you think? For the blue dot, what current goes into the blue dots? I1. Okay. So I have I1. Are there any other currents going into that dot? Nope. Okay, so that's all the current in. Now that needs to equal all the current out. So since I1's the only one going in, I2 and I3 must be the ones going out, right? Okay. So I1 equals I2 plus I3. Now a good check on this is to look at the other junction over there and make sure this matches up. So for this other junction, the black dot I made, what currents are going into the black dot? I2 and I3. And is I1 coming out of the dot? Okay, so once again, I2 plus I3 equals I1. And so you notice this is the same relation we had before. So our junction rule makes sense. Sound good? And if that sounds good, we did the junction rule. Now let's write down the loop rules. Now you can make a loop rule for any closed circuit. You can go through this any closed loop you can make. The loop rule has to be true, because basically the loop rule just says that if you start off at a certain voltage and you trace around a loop and you end up at that same spot, it needs to be the same voltage. So the 3 loops that we're going to look at, which way do they want us to go? Half a second, let me just make sure I'm, okay, 3 loops that I want to look at, that loop, do they care about the other loop? Okay, this loop, and there's a third loop you can go through. You can go around the outside, and we're going to talk about that one last. Okay, everyone pretty happy so far? Okay, let's do the red loop. Let's start right here. We're going this way. There's I1, there's I3. When we hit this resistor 2, are we going with the current or against it? So we're going that way across this resistor. Which way is I2 going? Okay, so we're going with the current. And when you go with the current across a resistor, do you gain voltage or do you lose it? And that one's okay. You lose voltage. So the convention is when you go across the resistor with the current, you lose voltage. If you're going against the current, you're going to gain voltage. If you're ever confused, go back to the simplest possible thing you can and think about, okay, well, I know the current's going this way, and so if I go around that way, I need to go from 6 volts to 0. So I'm dropping current, dropping voltage there. Okay. Okay. All right. So I'm going across this resistor. I'm dropping voltage. So I'm going to remember that V equals IR. So as I'm going across R2, the voltage I'm dropping is the current through it, which is I2, which we labeled, times R2. Okay. I don't like this. I don't. Let me hold off on that step. That's too much. Minus voltage R2. That's easier. Okay. Okay. We go through R2. We hit this battery. Battery 1. We're going from the negative side of the battery to the positive side. So are we gaining voltage or losing it? Are we going to a higher voltage or are we going to a lower voltage? Yeah, because if we assume the negative side is held at 0, the positive side would be higher than 0. So we're going to add, what was that one? EMF 1. Red loop. Okay, we got across there. We're hitting this little R1. Are we going with the current or against it? With. Okay, so we're dropping voltage. So minus V little R2. Okay, keep going through here. Down, around. Okay, we hit R1. And now where are we going, with or against the current? With the current. Okay, so minus VR1, exactly right. And then we go through it, we hit the spot that we started, so we know whatever we added or lost, it needs to add up to 0 now. Okay, so far so good. Okay, and now I'm going to do the let's look at the current times the resistance. So for voltage R2, we have I2, we have R2. So this is minus I2 R2. For the battery, we don't care what current's going through it. We just have the battery voltage. How about little, that's R1. That's the sort of thing that will really hurt. As you're going through little R1 up there, what current do you, what should I label the current? And your choices are I1, I2, or I3. Still I2, because that's this guy right here, right? Yeah, and since it doesn't like combine with anything else, it's still just I2. Okay, so minus I2 R1. Okay, and then we're down at this R1 at the bottom, and what current's going to go through that one? I1, right? So this is minus I1 R1 equals 0. Okay, is that reasonable? All right, I would like to point out that we are, as always, building up a system of linear equations. We're looking for I1, I2, and I3. I have one equation with all 3 unknowns. I now have a second equation with at least 2 of the unknowns. Since I have 3 unknowns, I need at least one more equation, right? And so that brings me to my green loop. And let me erase some things just because there's a lot going on in my diagram at this point. It's messy. Okay, that's better looking. Okay, now let's look at the green loop. So the green loop, we're gonna start right here and we're gonna go down. By the way, for your loops, you can choose whichever direction you want to go around. It won't matter. So just as long as you start and end at the same place, you'll be good. And in fact, why don't we go around the other direction for fun? Do I have a resistor there? No. Okay. Okay. We're gonna start here. We'll go this way. So when I hit resistor 1, am I going with or against the current? I'm going against it. So that means I'm going to add the voltage instead of subtract it. So green loop. We're adding VR1. Okay. We keep going around. All right, we're hitting I3. So R3, am I going with or against the current in this one? Still, excellent. Yeah, still going against because that's I3. So we have plus V R3. Okay, I continue around. How about little r2? Am I going with or against? Against. Okay, adding the little r2. I hit the battery. I'm going from positive to negative here. So should I add or subtract this voltage? Subtract. Okay, and I keep going around. I end up where I started, so now I know to set the whole thing equal to 0. And in the same way that we figured out the currents for the red loop, we're going to do the same thing for the currents for the green loop. So looking at resistor 1, we say I1 is going through R1. So let's just replace this with an I1, R1. How about R3? What current is going through R3? I3. So we'll take that one and replace it with I3, R3. How about R2, this little R2? Still I3. And I would like to point out that while generally your naming convention, you should try to be like stick the current with the same number as the resistor, it's not always going to work. So don't stress too hard about that. Okay, and that adds up to 0. All right. So with this, we have 3 equations, we have 3 unknowns. That's enough to solve this problem. Sound okay? But really quick, I want to talk about this yellow loop that I have around the outside. Let's go through this yellow loop. So I'll start the yellow loop right there. We'll go through this battery. Is the battery positive or negative? Positive, okay. The resistor 1 right there, positive or negative? Negative, because we're going with the current. So minus I1, R1. No, wait, I2, that's I2. Okay, I go across, I go down, I hit R3, positive or negative? So positive, perfect. So positive I3, R3. Okie dokie. Keep going around. R2, positive or negative? Positive. Plus I3 R2. Battery 2, positive or negative? Negative, because you're going from the positive end to the negative end, so you should be going to lower voltages there. So I'm subtracting E2. Okay, one last one, R2. Add or subtract? Yeah, going with the current, I subtract. Minus, was that I2? That's I2, R2. R2. And I'm back to where I started. So this adds up to 0. Okay, let's look at this. Now I have 1, 2, 3, 4 equations for 3 unknowns. What's it called when you have too many equations for your unknowns? It is a fancy word that means your system is overspecified. That's a bad thing. However, usually what it means is that you don't really have too many equations. One of your equations is just a combination of some of the other ones. So looking at this equation, let me pull my red loop over here. So red loop minus I2 R2 plus E1 minus I2 R1 minus I1 R1. Okay, there's my red loop. And then adding my green loop to that. So that was red. Adding the green, I have I1 R1, I3 R3, I3 R2, and minus E2. Okay, so this is the green one, this is the red one. If I add these two together, what's happening to my I1 R1 in this case? They're going to cancel out. And now let's look at this. I have a minus E2, minus E2. I have a plus I3 R3, plus I3 R3. I have a plus I3 R2. I have a plus I3 R2. Minus I2 R2. There's my minus I2 R2. Plus E1, minus I2 R1. And that's the whole thing. Right? So this yellow loop that we got from going around the outside is really just the equations we got for the red and the green added together. And so it's not adding anything to our knowledge. It's not helping us at all. And so while the outside loop, totally valid, like it's physically correct, you can write down the equation, it's really not going to help you any. Does that make sense? Okay. Okay. Now that we have these things, what are we going to do with them? Well, if you knew, so you notice the one thing they didn't give us what R1 was. So we'll solve for whatever they want us to solve for in a second. Basically, if you knew R1, you could just find I1, I2, and I3. And a lot of times when you're looking at these problems, notice that solving for anything here is not going to be super pretty. This isn't like a nice problem. In your engineering classes, you will learn how to put this into a matrix, into your calculator or MATLAB or Mathematica, and it'll just solve it for you. And it'll be very nice, and you won't have to think that hard. Sounds okay? Otherwise, you're just back to doing solving linear equations, just not a pretty one. Sound okay? Okay. Meanwhile, what this problem does, since we have time, what this problem tells you is that the current, it doesn't tell you R1, it tells you the current I2 is 0.02 amps. And it would like to know what I3 is. Sound okay? Okay, and so at this point, you start solving, and so you say, okay, I know things I know. I know everything except R1. I know what I2 is. It would be nice if I could get down to something solvable. I want to know what I3 is. So I would, if I were doing this, I would take, actually might take the outside equation. Would I take the outside equation? I would. I would add the red to the green, because what that does is it eliminates R1 from my equations, and I didn't know R1, so that's nice not to have to think about ever again. And then I would say, well, I want to figure out I3, so I don't, and I want to figure out I3, and I don't know, and I do know I2, so I don't want I1 in any of my equations. Does that sound reasonable? I think I already have that. I think I can just solve this. Yeah, I can just, you say, yeah, we can take this and we can just solve it. So the way to solve this, since we're solving for I3, get I3 on one side, get everything else on the other. E2, I2, R2. Okay, so my two terms with I3 in them, right there and there. So I have I3, R3 plus R2. That sound good? I would like to notice that we're adding R3 and R2 as if they were in series, right? And in fact, they are in series. Everything that goes through R3 has to go through R2, which, by the way, is a simplification that you can make in these problems. If you want to, before you start solving, you can add all your resistors in series if you want. What you cannot do is you cannot start adding resistors in parallel. So since you have this weirdness with the batteries, you can't just say, well, R1 is in parallel with R2 and R3. That's not a valid way to look at it. Is everyone okay with that? Okay, so adding resistors in series, totally fine. Parallel, not fine. Okay, so there's my I3 on one side. On the other side, I will have minus battery 1 plus battery 2, and then I'm going to collect my I2s. So for my I2s, I'm going to have a plus R2 and and a plus R1. Okay, did I get everything? I'm legit asking, guys. I think I did. Yeah. Okay. If I didn't, we'll come back and find my mistake. And then you just divide by that resistance. and R2 plus R1 divided by R3 plus R2. Okay, and at that point, you can go ahead and plug in your numbers. I had minus that one, plus all of those, plus those two. Hey, I get it right. Okay, yes. And that is the right answer. Sound okay? If you guys are happy with that, would you like to do another another circuit and just not solve it, just write down the Kirchhoff loop rules? Okay, yeah, that's really the hard part here. Once you get that the rest gets a lot easier. Okay, number 16, and I actually really like this homework program because it had lots of problems where they just wanted you to write down the Kirchhoff's loops and they didn't want you to solve, which is really nice. Oh yeah, what is it? Oh, not negative I2? Okay, let's, okay, so I'm up here. Why is it plus I2? Oh, I moved them to the other side, so I added plus I2 to both sides, plus I2 times the resistor to both sides. Sweet. Okay, number 16. Okay, so we have complicated set of, well, that's the positive side of that battery. Okay, so we have this, and I have R3, R4, EMF 3, R2, EMF 2, R1, and EMF 1. And this one also sets the current for us, where this is I1, this is I2, and this is I3. Okay, first things first, let's write down our junction rule. So let's write down the junction rule for this bottom junction here. What current is going to be going into the green dot? Yeah, so the green dot's the junction I want to look at. What current's going into that junction? I3. And what current is going out of that junction? I1, I2. Okay. Okay, so that's what our junction rule should be. And since we don't have any extra loops besides the 1, 2, and 3, when we look at the top junction, we should get the same answer, right? Or for the top junction, I1 and I2 are going into it, and I3 is coming out of it. And now, is everyone okay with that? Do you want me to draw some more lines on this, or does that make sense? Okay, if you're not, let me know. However, if you are, you should be very happy here because we have, no matter which way you look at it, I3 equals I1 plus I2. Okay, so that's our junction rule. We're happy with it. now we're going to make our loop rules. And I'll have a green one and a blue one. So there's one loop. Here's another loop. And we're not going to bother with the outside loop because we know it's just going to be a combination of the green and the blue. Okay. For the blue loop, we'll start here and we'll start going around, and we hit this battery, and are we going to add or subtract that? We're going to subtract. All right, so when you go from the positive to the negative edge of your battery, you're subtracting because you're going to lower voltages. Okay, going around. Now we hit this battery, EMF 2, battery 2 here. Are we subtracting or adding that one? We're adding that one because we're going from the negative to the positive. So we're going from lower voltages to higher voltages. Okay, continue around. We hit this resistor 2 right there. Are we adding or subtracting it? We're adding. Okay, since the current that we set is going up, we're going to, and we're going down through the loop, we're going to add this current. And while we don't really know which way the current's going, actually, what's really important here is that we're being consistent between our junction rule and our loop rules. So whatever way you set the currents in your junction rule, you need to keep those for your loop rules. You said against, so we're adding across voltage R2. Okay. All right, going across here, through here. How about R1? Are we going to add or subtract that? Okay, subtract because I1 is the current going through R1, right? And if it was going this way, that means it was coming this way. And so we're going with that current, so we subtract the voltage. Okay. And then we hit where we started, so we know that we're done. And we add the whole thing up to 0. Okay. You guys seem pretty happy? Well then, let's do the same thing with the green. So we're going to start going up through this R2. Are we going to add or subtract it? Subtract, right? Because you're going with the current at this point. So you're subtracting that. Okay, we hit battery 2. Add or subtract? Subtract, perfect. Okay. We hit R3. Are we adding or subtracting that one? Yes. Subtract, because now we're at I3, right? And so it needs to go around like that. So we're subtracting R3. We hit R4, add or subtract? Okay, still subtracting. And notice that R3 and R4 are in series, so we could have added this together. And that's when we plug in our currents here, we're going to see that we'll have I3 times R3, I3 times R4, and so we'll easily be able to pull out the I3. Okay, we go through, and we hit battery 3, and do we add or subtract that one? Yeah, we add it, perfect, because we're going from negative to positive. All right, and we're back to where we started, so it all adds up to 0. Now the only thing you have left to do is you go through these equations and you plug in the currents and the resistances. So you look at R2, so voltage R2, where's my R2? Right there. And you say, okay, I2 is the current that's going through that one. So we'll just substitute in I2, R2. And then you go to R1 and you say, what current's going through that? Current 1. So I1, R1. And you be careful because most of the time you've probably set up your subscript so that your current matches your resistor, but you know it won't always match. And then the same thing with the green loop. We have R2 and we know I2 is going through R2. And then we look at R3 and I3 is going through R3. But I3 is also going through R4. So you don't make up an I4 to go with that. You just say, well, that's still I3. Okay. Is everyone happy with that one? There's one more of these in the homework. We can do it or we can move on. What do you guys think? I think you guys have this. Okay. Okay, cool. Online people, you happy? Any deep questions? And if not, those are Kirchhoff's rules. Okay, cool. Then let's talk about RC circuits. So this is kind of a weird subject because the idea behind DC circuits is we said they had direct current, right? Where in all of the problems we've done so far, the current has been constant. So like I3, it wouldn't change over time. So we have no time dependence to our circuits. Capacitors, though, are very time-dependent kind of components because you build up charge or you lose charge over time. So when you have an RC circuit, we're going to see a change in current for the longer that you have your circuit together. And so let's look at that. So a classic RC circuit has a battery because you need a power source no matter what. It will have resistors, that's the R, and it will have a capacitor, the C. And it's generally set up, sometimes not. We'll look at it. So it has two resistors. One for when you're charging your capacitor and one for when you're discharging your capacitor. So here I have this switch where it can be hooked up to the capacitor or it can be hooked up to R2. Sound okay? And so let's look at just when it's hooked up to the capacitor because that'll be the charging circuit. So when it's just hooked up to the capacitor, we won't even bother to draw R2 because nothing's going to be happening with R2. Okay. I'm going to say initially this capacitor is uncharged. So we're starting fresh here. R1 and C. So at time equals 0, the charge on the capacitor equals 0. If the charge on the capacitor equals 0, what can you tell me about the voltage across this capacitor? If there's no charge, will there be a voltage? No, right? So the voltage on the capacitor will be equal to 0. And we're going to remember this, our basic equation for capacitance, charge per unit voltage. Okay, okay. So our capacitor is uncharged. We flip that switch. All of a sudden, this capacitor is hooked up to a battery. And as such, charge wants to go around this circuit, right? And so one side of our capacitor starts getting positive voltage, the other side, positive charge, the other side starts getting negatively charged. So a little later, small t, let me say small t. What can we say? So now that we have that, we can no longer say that the charge on the capacitor is equal to 0, right? Now we're going to have some charge that's more than 0, but still probably small. Like it will take time to build up. And the same thing with the voltage across the capacitor. It's going to start to build up, but it's still in the small stages. Okay. What about if we run this circuit for a while? So I run the circuit, charge keeps going. What can you tell me about like a stopping point maybe? Like how do you know when the capacitor is fully charged? Okay. Well, let me ask you this question. What if I told you, hey, I've got the circuit, I've hooked it up for a while. Can you, like this is the circuit. What's the voltage across that capacitor? What would you tell me? Shall we run a Kirchoff loop on it? Let's run a Kirchoff loop on it. I'm gonna start here. And I'm gonna run across this battery. So we're adding the battery voltage, right? Then I'm gonna run across this resistor. And so I'm dropping the resistor. Then I'm gonna run across this capacitor. And since I'm going from the positive edge to the negative edge, I'm gonna drop the capacitor. And then I'm gonna get back. Say again? Say again? We're gonna lose the charge. Not quite. So what you should see though is that, yeah, okay, good. The battery voltage needs to equal the voltage across the resistor plus the voltage across the capacitor. What if I don't have any current going? What will my voltage across the resistor be if my current's not going? V equals IR. If I 0, what's V? 0. Okay. And so I'm hoping what you guys are going to see is that over a long amount of time, the charge on the capacitor is going to build up and it's going to start blocking the current. Because I have a positive voltage here and I have this positive voltage here. And so the charge won't know which way to go. When that current goes to 0, then the voltage of the capacitor is going to be the same as the voltage across my battery. Does that make sense? If I made a circuit that looked like this, would you be happier? Maybe. Yeah, it's the same. It's the same thing, but without the resistor, right? And so if you have no resistor voltage, that's the voltage across the capacitor better be the same as the battery voltage. Excellent. Okay. So after a long amount of time, I know that the voltage across my capacitor is going to equal the battery. And the charge across the capacitor at that point will be, you know, Q C times the battery voltage. No idea. You must have moved. They're very motion detected. Although most of the motion detectors don't work that well. So yeah, you really got to make big movements. No. Okay. So we see this progression of the charge and the voltage. Let's take a second to look back at the current. Because once the voltage across the capacitor is the same as the battery, what will the current be? So once we're out here, what will the current be? Well, let's draw some pictures. I can always draw pictures. I got lots of time. Okay, so if I have this situation where I have a battery and I have a capacitor, and I have 6 volts on my battery, and I got 6 volts on my capacitor, which way is the current going to go? And that's a trick question, because the current is, I like a 0. I think, yeah. Because current always goes towards a lower potential, right? But if there's no lower potential, your current's 0. Okay, so the current's 0 in that case. Given that, let's take this back a notch. What if I had let me compare 2 scenarios here. I have the initial situation where my capacitor was uncharged, so there's 0 volts across it, and then I have like some midway situation where I have like 3 volts. I've built up 3 volts worth of charge on it. Which of these situations would you expect to have more current going through this circuit? And what you should be thinking here is which one has a bigger voltage jump? I like the 6 to 0 over here. Situation A. Because we're let's go back to our waterfall analogy, right? So if all I have to go from is 6 to 3, I'll get some amount of water, but not as much as if I can go from 6 to 0. That'll have more energy to get through that circuit. Does that make sense? So that means that initially here, when the voltage on my capacitor is 0, I'm going to have the maximum amount of current. I can't have more current than that. And then here, my current will be somewhere between 0 and the maximum value, but it's decreasing. So basically what's happening here is I hook up my uncharged capacitor to my battery, and the current, just sees a 0 voltage on the other side, and it just starts going as much as it can. But the charge on the capacitor sees that current, and it starts building up its charge, where the charge is being built up proportionally to how much current is going through. More current, more charge. But what's happening is as the charge builds up on that capacitor, that's blocking the current. So as we get more charge over here, the current decreases. However, it's still moving. So it's not that it's going negative, it's just less of it is going. But since it's still going, there's more charge building up on this capacitor, which then again decreases the current coming from the battery. But it's still going, so my charge on the capacitor keeps increasing, which keeps decreasing the current. Does this make sense? You might think back to last semester, Physics 220, when we were looking at air resistance. Because air resistance had that same thing where you went a little bit faster as you fell, which increased your air resistance, which decreased your acceleration, which means your velocity will still increase, but it's by a smaller amount, which will still increase your air resistance a little bit, decrease your acceleration. And so each little time step, everything's still growing, but less and less and less. Okay. Okay, so we have this idea. And what we're going to want to do is we're going to want to find an equation of current with respect to time for this scenario. We're also going to want to find an equation of charge with respect to time, but that'll be much easier. And because I have this here, I want to make sure to show it so I don't forget it next week. Where I want to kind of show what this looks like. So what do I got? I got a light bulb, which is just like a resistor. I've got a 1 farad capacitor. So this is a big capacitor. And I've got my 6 volts. So right now, this capacitor is uncharged. I know because I can hook up my light bulb across it and nothing happens. So it's uncharged. You should always make sure of that when you're dealing with a capacitor, because just by being out, they build up charge just by statics. And so what I'm going to do is I'm going to hook this battery up in series with my resistor and my capacitor. And we're going to keep an eye on the light bulb. So initially very bright. And now as we watch it over time, it's going to get less and less bright. You can, for this light bulb, you can say that the brightness of the bulb is directly proportional to the current going through it. So whatever the brightness of the bulb is doing, that's the same as the current going through it. And I hope you see that we've died off. Okay. And so that's pretty much what we saw. We saw initially we should have a very bright maximum amount of current. Then our current should decrease until it hits 0. And so now what voltage should be across this capacitor? 6, yeah. Same as my battery. Now, because I want to do the demo, I'm going to do the discharging right now as well, where I'm just going to hook up. Now I have this fully charged capacitor. I'm just going to hook up my battery, my bulb across this capacitor. What's going to happen? Better light up, yeah. And so all the charge is going to want to leave all at once, right? Because it's got a very positive side and a very negative side. And the positive charges don't want to be next to the other positive charges. But then over time, you're going to see, well, as the amount of charge on the capacitor decreases, so does the current through the light bulb. Makes sense? And so this would be the discharging, where initially it's very bright. And then again, you see the exact same pattern, right? Over time, it's decreasing. And I'm also kind of hoping that you notice it goes from bright to not that bright pretty quickly. But once it's not that bright, oops, it takes a while to go completely out. So it spends a lot of time in this intermediary stage of decreasing brightness, but not decreasing that quickly. Okay. Everyone kind of happy on this one. All right. By the way, this is our experimental data. I did air resistance with my mechanics class earlier today. And it's harder to get experimental data on that one. So how much? Okay, I got time to set this up at least. Okay, so we want charge with respect to time. We want current with respect to time. And we are going to do a differential equation, which you guys have done in 220. But we're going to do this differential equation to solve for it. Sorry. Where am I? I'm going to be right here is where I'm going to be. But where I'd like to start is this Kirchhoff's law, which conveniently we've already written down. So let's write this down again. Note that this Kirchhoff loop, we didn't need to really know anything about what was going on in the circuit. We just said I'm going to go around, I'm going to write down all the voltages. When I get back to the beginning, the voltages need to add up to 0, right? I don't need an E1, I just need an E. So I have minus the voltage across the resistor, minus the voltage across the capacitor, all adds up to 0. Okay. Now what I want to do, since I want current and or charge, I'm going to start with charge. Okay, I'm going to start with charge. Since I'm going to find charge first, I need to take these voltages and I need to write them in terms of charge. Now, for the capacitor, that's pretty easy, right? I can just use my definition of capacitance, where the voltage across the capacitor will be whatever charge is on the capacitor times the capacitance. Times the capacitance divided by the capacitance. Sound okay? I can do algebra. Now I'm using a lowercase q here to kind of indicate that this isn't the total charge. This charge will change with respect to time. So this is a variable sort of thing. Now my resistor is a little bit more difficult, but I can go back to Ohm's law and look at Ohm's law, because Ohm's law gives me that the voltage across the resistor is the current multiplied by the resistance. And so again, notice that I put the current as a lowercase because I expect it to change over time. And also, I can relate current to charge. And does anybody remember the equation that relates current and charge? Also maybe time. It was a while back. Where it was just the definition of current. Remember, the definition of the current was change in charge over change in time. And if we were going to do calculus, we would say that's really the derivative of charge with respect to time. We're going to do calculus. So we can plug that in for charge. Okay, dq dt. Okay, I'm about to stop for the day, but let me say some things about this, because this is this is where we're going to start. Just so I think most of you are in my 220 class, and I probably spent an entire lecture talking about air resistance. And this is the reason I talked about air resistance in 220, because we're going to do the exact same thing for this capacitor. Because the thing with air resistance is we're looking at speed, how fast something fell. And what we found was the amount of speed, the magnitude of how fast you're falling depends, affects the rate of change that of your speed. So when you had a small speed, you had a big rate of change. And when you had a big speed, you had a small rate of change. So how fast you were falling affected how fast you'd be falling the next second. Or in other words, the derivative of your speed was related to the magnitude of your speed. Okay, we're going to see something really similar here, where the magnitude of the charge on the capacitor will affect how quickly the charge is collecting on the capacitor. Because initially, when the charge on the capacitor is very small, it's going to grow very quickly. But then later on, when the charge on the capacitor is big, it's only going to grow a little bit at a time. So the rate of change of the charge, or in other words, the current, will depend on the magnitude of the charge. Vaguely okay? Does anybody remember what function describes that idea? Where the derivative of the function is the same as the function itself. If you're not sure of this, I want to draw a picture or two in my remaining minutes. And I want to draw a picture of this current with respect to time, where we're going to have a maximum. Well, I'm sorry, I don't want to do the current. I want to do the charge. I apologize. Charge with respect to time. I want to do this guy over here, where I know that we're starting at 0. I know that we're ending up at the capacitance times the battery voltage. Capacitance times the battery voltage. So I know I'm going to end up here. So those are my ending points. And I know, like, as long as I don't disconnect it, it's just going to stay right there. But the function is going to describe how I get between these 2 points. So, like, is this going to be a linear thing where my charge builds up the same amount every second? Is it going to be a thing where my charge builds up quickly at first and then kind of slowly collects over time and slowly approaches this maximum value? Or is it going to stay uncharged for a while and then only after some amount of time sharply start picking up charge? Which one of these seems most likely? Who says red? No one. How about blue? No. Green? All right, I got some greens. That's the right answer. Good job. So the greens answer, various ways is that makes this curve very smooth, right? You always want your answers to be smooth and continuous because physics tends to be smooth and continuous. Also, this matches what we were talking about with initially the charge builds up very quickly because it has a big amount of voltage to drop through. But then as the voltage builds up, the current has to decrease, so you're not collecting charge as quickly. Just so you know, what this is going to give us is this is going to give us some exponentials. Where an exponential is one of those things where the derivative is the same as the function itself. And you're going to see this because absent, there's a couple constants running around here, but we have the first derivative of the charge and the charge in this equation. So the first derivative of the charge has to equal the charge plus some constants. Does that make sense? So we're gonna have some amount of exponentials in here. The exact amount we will talk about on Tuesday. Everyone pretty good? Okay. Don't forget your quiz. Your homework is not due until next Friday. And I will see you next week. Except for my lab students who I'll see in 15 minutes. Online people, are you guys good? Next week on Friday. Yeah, you will have a quiz. The quiz is over resistors in series and parallel and Kirchhoff's loops. No RC circuits on the quiz. Yeah, no, that's next week.